So we talked about the linear function, we talked about the quadratic function. I guess the next level up then is our cubic function. Now the cubic function has two different basic shapes depending on the type of cubic. Now the classic one we're used to, that one there, that's when it can be factorised as a perfect cube. There might be some constant out the front, but basically we can factorise it to be k minus a all cubed. The other one is that sort of curve where you see two turning points. So you have a maximum turning point and a minimum turning point. That would also be a possible cubic. And yet again, we can create from these two different basic cubics, we can create all cubics via translation, rotation, reflection, all those sorts of things. So how do you recognise this? Well, now we see that the highest power is 3 in one of the terms. And we can keep going. So polynomials in general, and obviously there's lots of different basic shapes for polynomials depending on what the highest power is. Anything though that can be factorised down perfectly, so to be a linear function all to the power of something. If it's an even power, we'll get a U shape. Only the quadratic is a parabola. Right? So the quartic so it's not a parabola, but it still has a U shape. And if it's an odd power, it will have that classic inflecting shape. And what we'll find is as the power gets bigger, our curve will get flatter at the base and steeper at the sides. So how do you recognise a polynomial? Well, all the powers should be integers. You don't have a polynomial where you have a fractional power. And in fact, they should be positive integers because you don't have polynomials with negative powers. The highest power of a polynomial we call the degree of the polynomial. All right, let's talk a bit about sketching our polynomials then. So we want to draw y equals some polynomial in terms of x. Just like the quadratic, just like the linear function, the y-intercept will be the constant number. So that's the first key piece. So if I wanted to draw this polynomial and I've got it all factorised and I want to work out the constant, of course you don't need to expand the whole thing out, because if I wanted to work out the constant it would have to be all the constant terms multiplied together. So I'll have 1 times -1 cubed times 2 squared, which gives me, there it is down there, -4 would be the y-intercept. Alright, the x-intercepts, so the roots, we solve the polynomial equaling 0. Conveniently, it's already factorised for me, so that makes life a bit easier. So we know we will have x-intercepts at -1 for the first factor there, +1, and then the other one will produce -2. Out at the extremities, so out at positive infinity and negative infinity, the polynomial will act like the leading term. And that's because we're dealing with such big numbers that really we're only concerned with the highest power, because the one to a power 1 less than that would be significantly smaller than the highest one once we're dealing with these huge numbers. So we only need to look at the leading term, and that will tell us where the polynomial will start and finish. And once again, I don't have to expand the whole thing out. I can go x times x cubed times x squared. What's that? X to the power of 6. So if we were going to draw x to the power of 6, we know we would get that classic U shape. So I know that this polynomial will start up there and will finish over here. Just like if I'd drawn x to the power of 6. Okay, is that enough information? I know we've got to go through these points. Actually, there's a bit more information there to tell. The actual roots themselves behave like the power of the factor. So if it's an even power, I know it's going to touch it with a U shape. So if it's power of 2, it would look like a parabola, power of 4, it would look like a quartic, and so on. So over here, x plus 2 is squared, so I know at -2, it's not actually going to cut the x-axis. It's just going to touch it and turn. And because it's starting up there, I know my curve must do something like that at -2. Odd powers will have that inflecting shape. So our one, there it is, x minus 1 cubed. So at +1, that will inflect through 1. We know it finishes up there, so it must go through like that. What else do we need to know? That should be enough to get a a sketch. There we go, that's what it actually looks like. The only other piece of information that would have been handy, I suppose, is where exactly that turns. Is it on the left side of the axis or the right side of the axis? For this stage, we're drawing a rough sketch. We're not going to worry about that. Once we start doing some calculus, we'll be able to locate those turning points precisely. All right. Circles. So every shape we've looked at so far are functions. The circle, of course, is not a function. So x squared plus y squared is the radius squared. This is the one where it's important that the scale is the same on both axes, because otherwise you're not going to get a circle. It'll look like an ellipse. Right? So circles are not functions. They're actually composed of two semicircular functions. How do you recognise it? Well, now when we look at the pronumerals, both of them are to the power of 2. But the other key important feature there is that the coefficient of x squared and y squared is the same. If they were not the same, say I had x squared plus 2y squared, I wouldn't get a circle. What would I get? An ellipse. You'd end up with an ellipse. If it was negative instead of positive, if it was x squared minus y squared, what would we get? Do we know that one? That's the word I'm looking for, hyperbola. You actually get a hyperbola, not in the classic position that we're used to seeing, but it would be rotated 45 degrees, and so it'd still have that shape, but instead of the asymptotes being the x-axis and the y-axis, well, for x squared minus y squared, it would be y equals x and y equals negative x, but depending on the actual coefficient, those asymptotes would change. So they would be hyperbolas. So functions that involve a square root then. So like we say, the circle is not a function. Often created when an independent variable is made the subject of the function. What do I mean by that? Let's draw up a situation. There's our semicircle. Pretend I didn't draw that. Okay, if I was to make y the subject of that, we would then end up with a square root. So that's what I mean by this. It often gets created when we're making subject of the formula. Here's another one. That would be y equals the square root of x. So how do you recognise it? Well, it's pretty tricky. You see a square root sign, that's going to be a bit of a giveaway. But if you're really unsure, square both sides. And then the basic shape's going to be revealed of what it is. So for instance, I didn't recognise that this is going to be a semicircle. So I see y equals the square root of the radius squared minus x squared. All right, let's square both sides, see what happens, and I end up with what we recognise as the equation of a circle. So I know it's a semicircle. Positive square root means top half. Negative square root would mean the bottom half of the circle. And so similar with our y equals root x, didn't recognise it. Square both sides, we get y squared equals x, and we recognise that to be a quadratic, so I know it's going to be parabola. That's it. Positive square root is the top half, negative square root is the bottom half of our shape. Okay.